All right, 7.2 example one. This is where we're actually going to deal with an absolute value function. Um, it gets more complex when it's not just y equals the absolute value of x. So we have to be able to deal with that. One of the nice things about A is that we don't actually need the graph for that. Pretty important in math that if we ask you to find a y-intercept, you have to remember that that means that x is equal to 0. So in order to find the y-intercept of this graph, y would be equal to the absolute value of 2 times 0 minus 3, which is y equals the absolute value of negative 3. And I know it's one of those things that often we just say, okay, that's 3, right? The absolute value of negative 3 is a positive. But the reason that it is because that absolute value is applied onto a negative number, the absolute value multiplies it by a negative 1. And writing that out a few times is really good because it really shows up quite a bit in the piecewise function notation that we're going to do later. Well, negative 1 times negative 3 is 3. So my y-intercept is at 0, 3. Very, very similarly for the x-intercept, when we look to find an x-intercept, then y is equal to 0. And if y is equal to 0, then 0 is equal to the absolute value of 2x minus 3. 0 is one of those numbers that's neither positive nor negative. The only way that 0 is equal to the absolute value of a expression is if the expression is equal to 0. And that's going to happen when I move that 3 to the other side. I get that 2x is equal to 3, dividing by 2 yields that x is equal to 1.5. So my x-intercept is at 1.5 comma 0. Now, for a linear function, if you have 2 points, you can connect them via a line and you have the graph. But absolute value functions are a little bit more complex. They change directions. And so to sketch the graph, I would recommend we use technology. Or in some cases, as you get better and better at this, you may be able to do D first. And if you have expressed it as a piecewise function, then you can graph both pieces of those functions. Now, what I did is I put this into Desmos. To get to that absolute value button on your calculator, you do have to hit math and then over to the number option. But what that graph looks like is this kind of V. And basically, this is the concept of an absolute value function. And we can plot really or look really closely at where these points are. That point right there is our y-intercept at 0, 3. And then down here, we have our x-intercept at 1.5, 0. From the graph, we can do the domain and range. There is no value of x that causes me to divide by 0 or take the square root of a negative, so we're just going to say that x is an element to the real. Every single x value is certainly okay to put into that function. The range is a different story. This has the lowest value here at y equals 0, and it doesn't have a maximum value. They don't actually put the arrows in there, so I'm going to draw them in. But that function goes forever upwards. So for my range, I'm going to say that y is greater than or equal to 0, and y is an element to the real. In this section of math in 20-1 math, that'll be the range of most absolute value functions. I don't want to say all, because if I added or subtracted after or outside of the absolute value, that range would change. Really, really recommended that you use your calculator for domain and range. Now, to do this with piecewise, it really just hinges on the idea of recognizing that sometimes this function is positive and sometimes this function is negative. Now, when I say this function, I'm talking about the expression 2x minus 3. And at least initially, one of the things I want to do is I want to graph y equals 2x minus 3. Now, I'm just going to draw it on the same graph to the right. And what that would look like is it would look identical to what I have on the board, except it would have negative values. So just a quick example, if I were to put 0 in for this x, I would get that y is equal to 2 times 0 minus 3. I would get that y is equal to negative 3, which is this point down here. Now, that point is on y equals 2x minus 3, but it's not on y equals the absolute value of 2x minus 3, because that negative 3 would be inside an absolute value symbol, and it would turn it into the positive 3 above. Now, that's a kind of the reason why this happens. Ultimately, all you have to do a piecewise function is say that the absolute value of 2x minus 3 can be represented, and I'm going to write this out as the two pieces. If we take the absolute value of a positive, it is the exact same expression. So 2x minus 3, untouched. If it was negative, we would multiply by whatever 2x minus 3 gave us by the negative up front. The last part of the piecewise function is that we have to, and we can use the graph for this, identify what values of x make 2x minus 3 positive and what values of x make 2x minus 3 negative. And I think the best way of doing that is to use the x-intercept. At the x-intercept, when x is 1.5, that's this point right here, the function is 0. 2 times 1.5 minus 3 is 0. But if I use an x that's larger than that, and I'm going to shade this in green, that this region would be defined as x is greater than 1.5. And then the region that I'll do in blue would be defined as x is less than 1.5. Now, the reality is that you can include 1.5 in either of the positive or the negative case, but as a general rule of thumb, we include it in the positive. So 2x minus 3 is positive, and therefore the same thing if we took the absolute value of it when x is greater than or equal to 1.5, and 2x minus 3 is negative in this blue interval right here when x is less than 1.5, which means the absolute value would multiply it by the negative located directly in front of our expression. So negative times 2x minus 3 occurs when x is less than 1.5. Now, the idea behind this is I want to graph these. I'm going to kind of just erase my graph. So you remember, you can always rewind and pause if you want to look at anything again. I want to actually draw where those pieces are. And so I'm just going to kind of color code this with, I think, just red and green. So this function I'll draw in red. Now, because it's only when x is greater than or equal to 1.5, there's 1.5, and then it follows my absolute value function for the rest. So that's the first piece. The second piece, which I'm going to put a little green asterisk beside, is going to be a negative times 2x minus 3. Now, essentially what that does is it changes the slope to a negative value and also changes the y-intercept, but it accounts for this piece right here. Now, because x is only less than 1.5, technically that green piece should have an open dot there, but that dot gets covered by the positive case. So the combination of the green and the red graph are the absolute value of 2x minus 3. These functions are a little bit tricky to deal with, really, really important. I'm going to show you in the last question how to access that button on your calculator and make sure you know how to use that. It is just in that math number menu, which I'm sure came up in 7.1.